Okay, hello, this is operating system CS471 571, and I want to talk about just enough to get you potentially looking towards homework 3B. Alright, so for homework 3B, the basic idea is I want you to get into the nitty-gritty details of how xv6 keeps track of virtual memory. Let's look at a picture. Okay, so this is a high-level picture that shows virtual memory over here and physical memory over here. And the idea is that my C program is using memory addresses and pointers and whatnot. And without the user program needing to know exactly how things are happening, the operating system is really in between here, that every time you try to load a variable, there's something that automatically happens in the CPU that's set up by the operating system to go to an appropriate part of physical memory where that really is. Okay, so every user program, we did an example like this, every user program thinks its data is down near address 0. It can't be that they all are down near address 0 because there can only be one thing at address 0 in real physical memory. So the way this view of the world works is that the user programs all have their own virtual memory. They all have their own mappings from, if you get an address like this in the program, that really refers to physical memory something else. So there's got to be a translation from a memory address from a user program that's a virtual memory address into an actual physical location where that is in real memory. Okay, and so what you can think of, let's see, let's take a little bit of notes. Memory address translation, sure. So we have something called a memory page. So a memory page is a block or a chunk or a block of memory that is all together in physical memory and in virtual memory. Okay, so in xv6, this is 4096 bytes, all right, is a page. What that means is each, so from 0 up to 4095, for those first 4096 bytes, those are guaranteed to be consecutive in physical memory. It may not be that my 0 is maybe not physical memory 0, but the first 4096 addresses that I use are going to be together somewhere. Okay, so that's a memory page. It's going to be together. So then what the address translation needs to do what needs to happen is given the page, given the virtual address page, convert that into a physical address page. And typically the way this would work, let's say we have a 32-bit memory address. Okay? And xv6, it's 32-bit. This would work the same if it was 64-bit, like current CPUs. So typically the, 12 the, 12 the, 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 specify which byte within the page. Okay, 12 bits. So note that 12 bits gives 4096 different bytes. Okay, 2 to the 12th is 4096. So out of the 32-bit memory address, the last 12 specify where on the page. All right, so the first 20 bits specify which page. All right, so in our memory address translation, what needs to happen, given a virtual address page, so given the first 20 bits of virtual memory address, convert that into a physical page. So that means 20 bits for, let's see, first 20 bits of physical memory address. The last 12 bits stay the same. Okay? So what does this mean? To be able to do this, how many different pages are there in virtual memory that we may have to specify if we're just going to keep an array? So one way to keep track of converting from virtual memory address to physical memory address would be just to keep an array for each possible one. So how many different pages are there in virtual memory? So that's 20 bits. 20 bits specifies a page. All right, so that means there's 2 to the 20th. So that's around 1 million pages. If you're in 64-bit land, it's quite a bit more than that. All right, so we could have a lookup table of all 1 million possible virtual memory pages. Okay, and then in that case, we could have a table like this, would take some number of megabytes. If we get into 64-bit memory addresses, it's a ridiculously larger number than 1 million, and there's no way we would even think about this. Even for 32-bit memory addresses, it turns out that we don't want to have to store this like this. So the way Unix and xv6 keeps track of these translating from virtual memory to physical memory page is by, let me pause for a second. Okay, so the way that Unix and xv6 handles the translation from 20 bits of virtual memory address to 20 bits of physical memory address is it does it in 2 steps. There's something called a page directory, and the first 10 bits of your virtual address specifies a location in your page directory. Okay, so how big does this page directory have to be? How many rows if there's going to be 10 bits of the virtual address? Okay, if there's 10 bits of the virtual address that tells me where I am in a page directory, that's 1024 rows. Okay, so xv6 we have this translation from virtual memory to physical memory pages is a two-level tree. The root of the tree is the page directory. There are 10 bits in virtual memory address to specify a row in the page directory. So there's 1,024 rows in the page directory. All right. Then the next 10 bits in the virtual address says the next level of the tree. So you get an entry in the first 10 bits says an entry in the page directory. So there's information in that row to say that there's a page table. So this root node of the tree is called a page directory. So we have a directory entry there. Then that directory entry will give information to get to another table where we have the next 10 bits specify a row in the page table. Then in the page table, finally, we'll have the physical address bits that we need to complete the address. Right, the last 12 bits doesn't get changed. We need to figure out what's the first 20 bits. So an entry in the page directory points at a page table. Page table is 1,024 rows as well. Okay. And then an entry in page table gives 20 bits of physical memory address. All right, I could ask a question. Doing things like this, how much memory does this two-level tree take? If we were just doing a lookup table, we'd have 1,000,000 rows. If we're doing it this way with a two-level tree, how much room does it take? Well, there's still potentially going to be 1,000,000 different entries. But what happens is what Unix and XV6 will do is it'll only create a page table when it's needed. So initially, when you start a process, let's say it doesn't have any memory. It actually is going to have at least kernel memory. But let's say it doesn't have any right even before you start it. So when it doesn't have any memory, what you can do, there's flags here in the page directory, and you just specify no, this is not valid, there's nothing there. If there's nothing there, then you don't really need to store any information about it. Okay, and then the first time you use a memory address, a virtual memory address, I'll go ahead and make sure that there's a spot in physical memory where I can store this information you're looking for. Okay, so what's cool here, one of the things that's cool, we can be kind of lazy and initially store in the page directory that none of the memory is present or valid. So first use of virtual memory address wakes up the operating system, and the operating system can find a spot for that virtual memory to live. All right. Once the process gets going, some of these, it's used some virtual memory addresses, and so the appropriate rows will get filled in. But it's likely to be the case that most of the rows in the page directory are empty. So the process never used a memory address that started with some of those bits. So it's likely that process doesn't use most of the page directory entries. And for those, right, for the ones that aren't used, we don't need to even store a page table. If I've said that the process has never used a memory address that starts with you know, the 10 bits 1023, then there's no memory address that starts with those 10 bits, so I don't even need to have a page table for that. Okay, how much space, here's a question for y'all, you can pause. How much space does the page directory take? So according to this picture here, there's 4 bytes per row. Okay, 4 bytes per row, and 1024 rows. So note the page directory is 1024 rows, 4 bytes each row, so 4096 bytes. It's convenient that that actually is the size of one page, right? We decided that one page in XV6 was 4096. That's not a coincidence. They picked those to be the same. So the page directory actually fits in one page of memory. And likewise, also a page table is 4096 bytes as well. That's also not a coincidence. The page tables themselves, the second level of the tree to handle the second 10 bits, 1024 rows, 4 bytes. All right, so what you need to do is read the second chapter in the XV6 documentation. Okay, this is all talking about memory and paging, and you want to read the appropriate chapters in O-Step as well about virtual memory. Okay, so that's the address spaces, memory, address translation. So there's going to be a lot more in here than we need just for our assignments, but read it when you want to take a break from coding or whatever. So roughly chapters 13 to roughly all of this, but we're only actually going to need about half of what's in there. You can start kind of skimming through. And then you can come back and work on this. Next assignment is going to be a system call to print information about the page directory and potentially about physical memory. To be determined what that's actually going to be, but you can already get started trying to understand what's going on, and you could already start working on some code to print some information about the page directory. All right, good luck. The page directory, note, each process has its own page directory. So whatever you print is going to be, in this first part, is going to be for one particular process, the one that's running. All right, good luck.